Somewhere past the orbit of Neptune, 4 billion miles from the nearest streetlight, there is a rock that NASA has looked at exactly once with real interest, and then quietly moved on. No press conference, no follow-up mission, no headline. Just a string of letters and numbers buried in an archive, 2000 YV137. If you've never heard that name, you're not alone. Almost nobody has. And that, right there, is the first strange thing about this object. Because everything else out past Neptune that behaves the way this one does has gotten attention. This one didn't. This one got a single line in a database, and then silence. Let's start with what we actually know, because the facts alone are strange enough before anyone starts speculating. 2000 YV137 is a trans-Neptunian object, one of thousands of icy bodies drifting in the frozen suburbs of our solar system, past the orbit of Neptune, in a region so distant that sunlight takes over 5 hours to reach it. Most of these objects are unremarkable, frozen rubble, leftovers from the birth of the solar system, tumbling through the dark in silence, doing nothing, going nowhere, changing nothing. Astronomers catalog them by the thousand, note their orbit, and move on to the next one. That's the job, that's the routine, that's what should have happened here too. It didn't. 2000 YV137 was discovered in December of 2000 during a routine sky survey, the kind of automated scan that photographs the same patch of sky night after night, waiting for something to move against the fixed backdrop of stars. Something did move, a faint smudge of light, barely above the noise floor of the telescope sensor, crawling across the frame at a rate that told astronomers exactly one thing. This was big and it was far. Standard stuff at first. The object got its provisional name, the way every new discovery does, a jumble of numbers and letters that nobody outside the field will ever memorize, and it went into the queue for follow-up observation. That's where it should have ended. A few more images, a refined orbit, a size estimate, maybe a mention in an obscure academic paper that 3 people will ever read. Instead, something about the follow-up observations made astronomers sit up. The orbit didn't behave. Objects out in the Kuiper Belt, the vast ring of icy debris beyond Neptune where 2000 YV137 lives, tend to follow orbits shaped by billions of years of gravitational nudging from the giant planets. Over that kind of timescale, chaos smooths itself out. Orbits settle into families, into patterns, into predictable rhythms that astronomers can model with startling precision. It's one of the quiet miracles of celestial mechanics. Give scientists an orbit, and they can tell you where an object was 1,000,000 years ago, and where it will be 1,000,000 years from now, accurate to within a rounding error. 2000 YV137 broke the pattern. Its orbit is tilted at an angle that doesn't match its neighbors. Its path swings from a point relatively close to the Sun out to a distance so extreme that it spends most of its multi-century orbit in near total isolation, farther than any other known object than Manhattan is to Tokyo. And the eccentricity, the measure of how stretched out and non-circular an orbit is, sits in a range that resonance models struggle to explain cleanly. It's not just unusual, it's the kind of anomaly that in any other field of science would trigger immediate, well-funded, headline-generating follow-up. Compare it to Sedna. You've probably heard of Sedna, the strange red remote world whose bizarre orbit reignited serious scientific debate about a hidden 9th planet lurking in the outer solar system. Sedna got telescope time, Sedna got media coverage. Sedna got its own Wikipedia rabbit hole and a dozen documentaries. 2000 YV137, discovered around the same era with an orbital anomaly that some researchers have quietly noted is just as puzzling, got almost nothing. A handful of archived images, a provisional designation that was never even upgraded to a formal name, and then nothing. Why the difference? Here's where the story gets uncomfortable, because the honest answer isn't a cover-up in the cinematic sense, it's something almost worse: indifference dressed up as bureaucracy. Every year, telescope time is rationed like water in a drought. Every observatory on Earth and every space-based instrument in orbit has more requests for observation time than hours in the schedule. Committees decide what gets studied and what gets shelved, and those decisions are made by humans, with human priorities, human blind spots, and human budgets. An object that doesn't fit neatly into an ongoing research narrative, that doesn't have a compelling one-sentence pitch, that isn't already famous, it loses every time. Not because someone in a windowless room decided the public shouldn't know, because nobody with the power to green light another observation ever had a strong enough reason to bump it up the list. But that explanation, as mundane as it sounds, raises its own uncomfortable question. What happens to the objects that fall through those cracks? How many 2000 YV137s are sitting in archives right now, flagged as anomalous by exactly one overworked researcher and then forgotten because nobody had the bandwidth to chase it further? Because here's the thing that should unsettle you. The orbital weirdness isn't even the strangest part of the file. In 2007, 7 years after its discovery, a small team briefly revisited the archived images of 2000 YV137 while cross-referencing outer solar system data for an unrelated survey. What they noticed, buried in a technical note that never made it into a major journal, was a brightness variation that didn't match anything they expected from a simple icy rock tumbling through space. Most trans-Neptunian objects vary in brightness in a predictable way. As they rotate, different surface features, an icy patch here, a darker mineral deposit there, catch the sunlight differently, producing a light curve that rises and falls in a smooth, repeating rhythm. Astronomers use that rhythm to calculate rotation speed, shape, sometimes even surface composition. It's one of the few tools available for studying an object that will never be visited, never be photographed close up, never be anything more than a moving point of light 4 billion miles away. 2000 YV137's light curve wasn't smooth. It had an irregular dip, a sudden sharp decrease in brightness that didn't fit the rotation pattern already established from earlier images. Then, just as suddenly, the brightness returned to its expected baseline. One explanation, the most boring and most likely one, is instrumental noise, a cosmic ray hitting the detector, a processing artifact, the kind of glitch that shows up constantly in astronomical data and gets filtered out as a matter of routine. Another explanation, floated quietly and never seriously pursued, is that the object might not be a single body at all, but a binary system. Two objects orbiting each other so closely that from Earth they appear as one point of light, occasionally eclipsing each other and briefly dimming the combined glow. Binary trans-Neptunian objects are real, and they're actually fairly common out there. It wouldn't be shocking. It would just require someone to go back and check. Nobody went back and checked, not seriously, not with a dedicated observation campaign. The technical note sat in an obscure appendix, cited by almost no one, referenced in exactly one follow-up paper that mentioned it in a single sentence before moving on to its actual subject. The mystery wasn't solved. It was simply abandoned. And this is the story of 2000 YV137 stops being about one small icy rock and starts being about something bigger, about how much of our own solar system remains genuinely, embarrassingly unexplored. Consider the scale of what we're dealing with. The Kuiper Belt alone is estimated to contain hundreds of thousands of objects larger than 60 miles across, and that's before you factor in the far larger, far more diffuse Oort cloud that may extend nearly halfway to the next star system. We have detailed data, real data from real instruments on perhaps a few thousand of those objects. The rest exist only as statistical inference, mathematical placeholders in models that tell us they should be there without telling us what they actually are. 2000 YV137 isn't an exception to how we study the outer solar system. It's the rule. It's what typical actually looks like once you strip away the handful of famous objects that get all the funding and all the attention. That's the uncomfortable truth hiding underneath the clickbait question of why NASA won't talk about this rock. NASA isn't hiding anything about 2000 YV137 in the sense of a locked vault and a classified stamp. What's actually happening is quieter and, in its own way, more disturbing. An entire category of solar system objects that could rewrite our understanding of how planetary systems form, how binary worlds arise, how objects migrate and settle into strange resonant orbits. An entire category sitting largely unexamined because the machinery of scientific funding simply cannot keep pace with the sheer number of things worth studying. There's a term astronomers use half-jokingly for objects like this: orphan discoveries, found once, flagged as interesting, and then never revisited because no one owns the follow-up. No dedicated team, no ongoing grant, no institutional momentum. The system produces orphans by design, not by malice. And once an object becomes an orphan, the odds stack against it fast. Every observatory with the resolving power to study something 4 billion miles away is booked, often for years in advance, by proposals competing for the same limited nights of clear, dark sky. A researcher who wants to chase 2000 YV137's brightness anomaly has to write a formal proposal, justify why it matters more than 100 other competing projects, survive a peer review committee that has seen 1,000 "this might be interesting" pitches before, and then wait, sometimes a year, sometimes several, for an approved slot to actually open up. Most give up before they start. The ones who don't give up are gambling months of their career on a rock that might turn out to be nothing more than a stray cosmic ray hitting a detector 25 years ago. That's not a conspiracy. It's worse, in a way, because it means there's no villain to blame and no secret to expose. It's simply what happens when the volume of things worth studying vastly outpaces the number of hours available to study them. Astronomers have a phrase for the entire unexplored majority of the Kuiper Belt, the known unknowns. We know the objects are there, we know roughly how many, we know some fraction of them will turn out to be genuinely strange. Statistically, it's almost guaranteed. We just don't know which ones yet, and we don't have the observational bandwidth to check them all before the funding cycle moves on to the next hot topic. Here's a number that puts the whole situation into perspective. Since its discovery in 2000 YV137 has been directly observed, according to the Public Archive, on fewer than a dozen separate occasions across 25 years. 12 data points scattered across a quarter century, describing an object that takes roughly 3 centuries to complete a single orbit of the Sun. Extrapolate that rate forward, and you start to see the real scale of the problem. At the pace outer solar system objects are currently being followed up, some of the strangest bodies we've ever catalogued may not receive a second serious look within any of our lifetimes. not because anyone decided they weren't worth it, because the queue is that long and the sky is that big and the funding is that thin. Which brings us back to the binary hypothesis, because it's worth sitting with for a moment just how much a single confirmed answer would actually tell us. If 2000 YV137 turns out to be a close binary, two icy bodies locked in tight mutual orbit, briefly eclipsing one another during that anomalous brightness dip recorded in 2007, it would join a growing list of trans-Neptunian binaries that are quietly reshaping how astronomers think about the outer solar system's early history. Binaries like this are thought to form during the delicate, chaotic infancy of the solar system, when the outer disk of gas and debris was dense enough for pairs of smaller bodies to capture each other gravitationally and settle into a shared orbit that has survived essentially unchanged for 4.5 billion years. Every confirmed binary is a frozen snapshot of that ancient, turbulent era, a fossil record written not in stone, but in orbital mechanics. Confirming another one wouldn't just resolve a minor anomaly, it would add another data point to one of the biggest open questions in planetary science. Exactly how chaotic and exactly how crowded the early solar system actually was.
And here's a detail that tends to land hardest once people hear it. The technology to properly resolve the mystery of 2000 YV137 already exists. The James Webb Space Telescope, currently studying targets across the observable universe, has instruments sensitive enough to nail down the object's size, its surface composition, possibly even confirm or rule out the binary hypothesis in a matter of hours. Hours, not years, not a new mission, not billions of dollars. A single observation slot on an instrument that already exists, pointed at coordinates that are already known. And yet, as of now, no such observation has been scheduled. Not because it's technically difficult, not because anyone decided it wasn't worth knowing, simply because in the vast queue of competing priorities, an anomalous rock discovered in 2000 has never once made it to the top of anyone's list. Maybe that changes soon. Maybe some early career researcher, digging through archived data the way that 2017 did, stumbles across the same light curve, gets curious, writes the proposal, and finally gets the telescope time that's been sitting just out of reach for over 2 decades. Maybe 2000 YV137 turns out to be exactly what the boring explanation predicts: an ordinary icy body, an unremarkable orbit quirk, a data glitch mistaken for mystery. That happens far more often than the dramatic alternative. Most anomalies, when finally investigated, resolve into something explainable. That's not a disappointing outcome. That's how science actually works, one boring answer at a time, slowly closing the gap between what we've observed and what we understand. But maybe it isn't ordinary. Maybe it's a binary world, locked in a slow gravitational dance no human eye has ever resolved. Maybe its tilted, stretched orbit is a fingerprint left behind by something we haven't found yet, a distant planet, a close stellar flyby in our solar system's ancient past, a gravitational encounter lost to 4.5 billion years of drift. We don't know, and that's the actual point of this story. Not a cover-up, not a secret, just a gap, an honest, uncomfortable gap between how much is out there and how little of it we've actually looked at. Right now, tonight, 2000 YV137 is somewhere in the black beyond Neptune, moving along its strange, tilted path exactly as it has for billions of years, utterly unaware that it briefly caught human attention in the year 2000 before being quietly set aside. It isn't hiding from us. It never was. We simply haven't gotten around to looking again. And somewhere in that gap between discovery and understanding, between the single photograph taken in 2000 and the follow-up observation that still hasn't happened, is the real story the internet keeps turning into a conspiracy. Not a cover-up, a blind spot. One of thousands scattered across a solar system we've barely begun to map, waiting for someone to finally point a telescope back in the right direction and ask the question nobody bothered to finish asking 25 years ago. What exactly is out there?